All right, greetings and salutations. So last time we talked a little bit about the basics of propositional logic. So we covered, you know, covered what a proposition was, and we covered little bit about the logical connectives used to um, take atomic statements, so the simple P's and Q statements, and turn them into more uh, compound statements. So we covered not P, P and Q, P or Q, and the conditional P implies Q, or if P then Q. So today I want to pick up where we left off and first talk about the biconditional statement. So if we look here, this right here is called a conditional statement. If P, then Q. So P is called the hypothesis and Q is called the conclusion. A biconditional, so a biconditional is similar. We write this. So the arrow in this case is going both ways. And we read this as P if and only if Q. P if and only if Q. So what does this mean? Really, this biconditional is, you can think of it as shorthand for P implies Q and Q implies P. So this statement right here really means the same thing as this statement, and we can see that by using a truth table, right? But first, I wanna mention really quick. We read this as we say P if and only if Q, because this statement combines both if P then Q and if Q then P in it. So the statement P only if Q, that's what this means. So P only if Q. That's what this statement is right here. And then this part of the statement is P if Q. So this just means P if Q just means if Q then P, right? So that's what this is saying right here. And then P only if Q means, P can't happen without Q. So that's saying if P happens, then Q must also happen. That's why we have P only if Q. And then this is the and right here. So we have P if and only if Q. That's where that comes from. And if we are to draw a truth table out here, this is what it would look like. So we have P, Q, say P implies Q, and then Q implies P, and then P if and only if Q, which again we know is the same thing as P implies Q and Q implies P. So we draw out the truth table. If we look back at what we learned last time, so let me write out the truth values for the atomic statements first. P implies Q is false exactly when P is true and Q is false, when the promise is broken, right? And the hypothesis is true, but the conclusion is false. If we go back up here, this P implies Q is false exactly when P is true and Q is false. So that's what we're going to write here. P is true and Q is false, this is false. And it's true every time else. Similarly, for Q implies P, it's the roles are reversed. So Q implies P is false exactly when Q is true and P is false. So that's this row right here. It's true everywhere else. And remember, P if and only if Q is an AND statement. It means P implies Q and Q implies P. Now, when will this AND statement be true? If we go back up here, instead of saying P and Q because we're already using P and Q, let's call them A and B. A and B are true exactly when A is true and B is true, right? So this biconditional statement will be true exactly when this is true and this is true. Oops. And that's this first row right here and this last row right here. It's false everywhere else. Now, if we look at this, we can really just say this biconditional statement, P if and only if Q, is true exactly when P and Q have the same truth values. We look right here, when both are false or both are true, that's when this biconditional is true. When they have mismatched truth values, so one is false, one is true, then this biconditional is false. So let's look at a real world example of this biconditional statement. So say that Bob is taking a discrete math class, right? Bob in a discrete, I don't know what I wrote there. Discrete math class. Amazing handwriting. And say that this class it's a weird class. There's only, the whole semester grade is based only on the final exam. So the final exam is worth 100% of the grade. Right? Now let P be the statement. Bob gets an A on the final exam. And let Q be the statement. Bob aces the class. Then I claim P if and only if Q. I say Bob gets an A on his final exam if and only if he aces his class. And why do I say this? Because let's go to this first part. So that's it's just saying P implies Q and Q implies P, right? So let's say Bob gets an A on the final exam. Let's consider this statement first, and let's suppose that P is true. Bob gets an A on the final exam. Then because the final exam is 100% of the grade, it's the whole grade, if he gets an A on his final exam, of course he's going to get an A in the class, right? So we have this statement holds. And on the other hand, if Bob aces the class, if we have Q, suppose Bob aces his class, then that must mean he got an A on his final exam, right? Because the final exam is the whole grade. So this statement holds. That's why we can claim Bob gets an A on his final exam if and only if he aces the class. Now suppose that's when P and Q are both true. Suppose that P and Q are false. It also works out. Say that Bob does not get an A on his final exam. Well, then it's impossible that Bob gets an A in his class. He can't ace his class, right? Because the final exam is the grade for the whole class grade. And on the other hand, the converse, if Bob does not ace his class, that must mean he did not get an A on his final exam. So we can see that P is true exactly when Q is true. P is false exactly when Q is false. So all this time I've been saying the phrase exactly when. From now on, now that we have this biconditional statement, I'm going to start saying if and only if. So, Bob aces class, or Bob gets A on his exam if and only if Bob aces class. And as you can see here, I wrote this this IFF. This is just shorthand for if and only if. Oh, whoops. This is just shorthand for if and only if. Now that we covered now that we covered biconditionals, I want to get into combining these logical connectives that we learned. So, not, and, or, and then these two implies and biconditional. I wanna combine a few of these logical connectives into creating more complicated propositional statements. And yeah, so let's do that. All right, so let's say we have 4 atomic statements, P, Q, R, and S. So let P be the statement. Sally sees her friends. She gets to hang out with her friends. And let Q be the statement. Sally has a soccer game. Let R be the statement. Let R be the statement that the soccer game gets rained out. So it gets canceled because of too much rain. And let S be the statement, Sally is happy. So I can make the more complicated, so I have these 4 atomic propositional statements, and I can make the more complicated statement by using connectives. I can say P or Q and not R implies S. So what am I saying here? I'm saying if Sally sees her friends, or Sally has a soccer game and the game does not get canceled, then Sally is happy. That's this. And as you can see over here, I drew parentheses around the Q and not R. So before we get more into this, I want to explain the order of operations of these logical connectives. So in math, whenever we're doing arithmetic, we have PEMDAS or GREMDAS or something, right? Where parentheses come first, then exponents, then multiplication, division, then addition, subtraction, and so on, right? We have something like that with logical connectives as well. So the not symbol gets first precedence, then comes and, then comes or, then comes the implies single arrow, and then comes the two-sided arrow. So really if you want to draw out parentheses explicitly for this statement right here, it would look something like this. You want to draw out all the parentheses to make sure you get the groupings correct. It would look like this. So this implication comes last, right? So we have this whole thing implies S, and then within this hypothesis, within this first big statement, we have the we have what was I saying? Oh yeah, we have this. We have well, I drew the parentheses around the I drew the parentheses around the end, but actually I didn't even need to draw them here, so I could actually just to illustrate what I mean. I could write this. This is the uh, exact same thing. So this statement right here, P or Q and not R implies S, is the same thing as this statement right here. So the implication comes last, and then comes the or. So we have this P or this statement right here, Q and not R. And then within the Q and not R, we then have the and. So Q and not R, and then the not as first precedence, so it gets grouped together right here. So if you really want to draw parentheses, that's how you do it. And if you want to say something like A and B or C, this statement right here means the same thing as A and B or C. If you want to draw the parentheses differently to mean the B or C are grouped together, then this is a completely different statement. This means A and B or C. So that's just some order of operations right there. Now let's get into what this statement means. So I'll draw it again right here, and I'm going to draw it with the parentheses this time. P and P or R S. So I'm saying if Sally, what did I say? Yeah, if Sally gets to see her friends, or if Sally has a soccer game and the game does not get rained out, then if this thing is true, if Sally gets to see her friends, or Sally has a soccer game and the game does not get rained out, then Sally is happy. So that's how we can combine these logical connectives to make more complex propositional statements. All right, so now I want to get into some more, I want to get into logical equivalences. So we have all these statements, right? Like we can make all these statements using these connectives as we've seen right here. But sometimes we can have statements that are technically different, but have the same true. They're logically equivalent, meaning when one is true, then the other is true, and vice versa. It's kind of like the if and only if, right? So For example, like this is a logical equivalence right here, a very simple one. P and Q is logically equivalent. We use these three lines to mean, the logically equivalent to Q and P. And uh, this is, a little bit more intuitive to understand because, saying A and B is the same thing as B and A. It's like the commutative law in addition, where if we have A plus B, it's the same thing as B plus A. 3 plus 5 is 8. That's the same thing as 5 plus 3. So we have this. We have this logical equivalence. And how can we show it? Well, we can just draw out a truth table. So if we have P, Q, P and Q, Q and P, we can we can check that P and Q, let's see, it's only true when P is Q and true is Q, and then false every time else. Q and P is true exact if and only if Q is true and P is true. That's this row right here. It's false everywhere else. And if we compare the entries in the truth table for this column and this column, we can see that they're the exact same, which shows us that this logical equivalence holds. Now, with that said, I want to get into some more complex or less intuitive logical equivalences, and I'm going to list a few out here. I'm going to start a little bit more. Actually, let's start with another not super unintuitive one. So the statement not P is logically equivalent to P. So if we have P right here, and we have not P, and then not P, right? This is the same thing as this right here. Well, see, P can only take on the values true or false. Then not P must be the opposite. So if P is true, then not P is false. Then if P is false, then not P is true. Then we have not P. So if not P is false, then not P is true. And if not P is true, then not P is false. Now we can check that this column and this column have the same truth values. So that shows this logical equivalence right here. Now I'm going to list out some more. These two in particular are very important. They're called De Morgan's laws. I hope I spelled that correctly. And those are these two logical equivalences right here. We have not P and Q is equivalent to not P or not Q. And on the other hand, the second one is not P or Q is equivalent to not P and not Q. So as you can see, these two equivalences look pretty similar. We have an and right here. The only difference is the ands and ors are flipped. If you look at this, if you look at law 1, law 2, the only differences are this and is replaced by an or over here, and this or is replaced by an and over here. Now I'm going to verify one, and I encourage you to verify the other on your own. So I'll verify the first one. Now, we're going to draw out a truth table for this. We have the statements P, statements Q, and we need a P and Q, right? P and Q. Then we tack on the not. So we have not P and Q. And we also have this not P and not Q and not P or not Q. So we have to add the not P, not Q. Right? We are basically building up. We are building up from the atomic propositions P and Q to the more compound propositions by adding one logical connective at a time. So we tack on this and first, and then we tack on the not to this P and Q, and then we tack on the not to the P, not to the Q, and then we tack on the or with the not P or not Q. This is a pretty big truth table. All we're doing when we are constructing truth tables, we just want to tack on one logical connective at a time. And in order to decide which logical connective to tack on first, well, you look at the order of operations and do it from there. So whichever operation has the highest precedence in this case, because the and P and Q is in parentheses, this has first precedence over the not. So we evaluate P and Q, and then we evaluate the not P and Q, right? In this second statement right here, we have that the nots take precedence. We want to draw parentheses. This is what it will look like. The nots take precedence over the or. So we tack on the not P, we evaluate not P, and we evaluate not Q, and then we evaluate not P or not Q. So draw the truth tables like this, and this is going to be a interesting true, false, true, true, false. So P and Q, as we've seen before, this will be true, this will be false, this will be false, false. And then the not, if we do a not P and Q, it's just the opposite of P and Q. So false, true, true, true. Now, when P is true, not P is false. P is false, not P is true. Same goes with Q. Then remember, the or is true if and only if at least one of not P or not Q are true. So if we look at the not P and not Q columns, at least one of them are true. Here, it's false. Now, if we look at this column right here, which is the first part of this logical equivalence, then we look at this last column right here, which is this statement right here, we can see that the truth values are the exact same. And that's how we know they are logically equivalent. And so I would encourage you to verify this second one on your own using the same template or a similar template. Now, we covered the commutativity. It's called commutativity when you can flip-flop the P and Q, Q and P. Commutativity of and, we covered the negation, double negation law. We covered the De Morgan's laws, which these are especially important, by the way, and I know it can seem quite these De Morgan's laws especially are not very intuitive. They can be tricky to understand at first. So, take some time to really study them and understand why they work. I want to list some more laws right here. So we have the commutativity of and. Now we also have P or Q is the same thing as Q or P. And I'm not going to verify these next ones that I list. I want you to do that on your own using the same method that we used to verify the last three laws that we went over. So we have this is the commutativity of or right here. Another law is we have an associativity law. So we have in arithmetic, a plus b plus c is the same thing as a plus b plus c. And we also have that when it comes to logic. So we have p and p and q and r is the same thing as p and q and r. We also have that with the or. We have P or Q or R is the same thing as P or Q or R. We also have a distributive law. So if you think about, if you want to think about the and symbol as being like a multiplication, so multiplication symbol like a times b, and if you want to think about the or as being like addition, where it's like a plus b, right? If you want to think about it that way, then this we have this distributive law in arithmetic where we go well, what was distributive? Oh yeah, so we have a times b plus c is or yeah, I mean, if you like this is just one way you could think about it for one distributive law, and then for the other distributive law you can think about the or being the times and the and being the plus. I'll one after the other. I'm getting ahead of myself here, but so if you want to think about it like this, we have a times b plus c is equal to a times b plus a times c. And similarly, we have this law in logic where the and distributes over the or. So we have P and Q over R is the same thing as P and Q or P and R. So as you can see, this multiplication matches up with and, this plus matches up with or. And on the flip side, we also have P or Q and R. It's the same thing as P or Q and P or R. And I'll even draw the parentheses here to make it more clear. But in this case, you don't have to draw the parentheses. In this case, you have to draw the parentheses because remember that the and takes precedence. So without the parentheses, this statement would become P or Q and P or R, which is not the same thing. So we need to draw the parentheses in the second statement right here, or second equivalence. Another logical equivalence that we have is this is an interesting one. So P implies Q. We've gone over that quite a bit. If P, then Q. That's actually equivalent. Again, this is not very intuitive, but that's equivalent to not P or Q. And you know what? This one I'm actually going to verify in truth table because I think it's quite interesting and I want to cover it. So we have P, Q, P or Q, not P or Q. So we have 4 combinations: true, false, true, false, true, true, false, false. So this would be true, this would be true, false, true. P is false, true, false, true. Then not P or Q is true if and only if one of these not P or Q is true. And that, in this case, it's true here, false here, and true here. And if we look at these two columns, P implies Q, then not P or Q, they're the same thing. All right, the next logical equivalence I want to go over is the contrapositive. So P implies Q. Again, this comes back again. P implies Q is the same thing as, well, not same thing. It's logically equivalent to not Q implies not P. And this is called contraposition. So this is the contrapositive of this. Right? You're basically flipping the P and Q around. We're also negating them. So this, if I say, if Bob is a cat, then Bob is a mammal. That's the same thing as saying if Bob is not a mammal, then Bob is not a cat. And if you look at it, it makes sense, right? If Bob is a cat, then surely he must be a mammal. And if Bob is not a mammal, well, since all cats are mammals, then how can Bob possibly be a cat? So, checks out. As yeah, so we have that. We also have the inverse of if and only if. So note that P implies Q is not equivalent to not P implies not Q. We do not have this. And another thing, P implies Q is also not equivalent to Q implies P. So this is called the inverse. This is called the converse. But what we do have is this is equivalent to this. We have not P implies not Q is equivalent to Q implies P. And if we can see why, because the inverse is equivalent to the converse. And we can see that up here. This Q implies P, P implies Q. Not P implies not Q, not Q implies not P. All we did was flip the P's and Q's around. We just flip-flop the P's and Q's, and we have the exact same equivalence here. But with if and only if, we do have that. So we have, with if and only if, we have P if and only if Q is the same thing as its inverse, not P if and only if not Q. We also have it's the same, it's logically equivalent to its converse, not, first no, not. P if and only if Q is the same thing as Q if and only if. So those are some logical equivalences that I think are important to know. I also actually I do wanna cover a couple other ones. This is, I want to cover tautologies and contradictions. Tautologies and contradictions. So what are tautologies and contradictions? A tautology is a propositional statement that will always be true. So something like this: P or not P. This statement will always be true. Why? Well, if we look at the truth table, well, this or statement will be true exactly when one of P or not P is true. That's both cases right here. No matter what, this statement is always true. And a contradiction is a statement that's always false. So something like P and not P. If P is true, then not P must be false, and therefore this whole and statement is false. If not P is true, then P must be false, and therefore this whole and statement is false. So this statement will always be false. So those are tautologies, and those are it's just one example of a tautology and a contradiction, right? But there are plenty more that you can look at. Yeah. Oh, and a couple other logical equivalences that I forgot to mention. These are, again, not too unintuitive. You can say P and P is logically equivalent to P. You can also say P or P is logically equivalent to P. I think those are just those are a little bit more intuitive than some of the other ones we carried, but still important to know. So next time I want to talk, this video is already quite long. Next time I'm going to, I don't know, I might go into deduction rules, or I might get into what predicates are. I'm not sure yet, but yeah, thank you for watching.